You got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. Yeah, I'm yours. Yes, you got my future in your hands, baby. I'm yours, and I'm gonna be yours. And here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. Oh, baby, I didn't do this all.
All right, everybody, let's get started today. Welcome. It is Friday, the 17th of April, the end of marking period 3, and we are here with a brand new buzz cut. Literally never had hair this short in my life, and it's time to do some physics. So let's get to it. I do want to note that there's apparently some kind of announcement at 2:30 today. This is again on Friday from Governor Hogan, so we're going to kind of be waiting to see what happens with the rest of the school year. I have my guesses, but we'll wait to find out. I do want to make a couple notes about the last day of marking period 3, provide some of the updates on AP exams in case you didn't hear them in the past, and then go over our capacitors FRQ, our Unit 2 FRQ, and frankly, we'll probably do more Unit 2 MCQs than Unit 1 because nobody told me that the link to this week's work was broken until I found out today. So no bug bounty for all of you. Yes. Let's get started. We are continuing to work our way backwards through this review. So today we are going over Unit 2. Which is capacitors, not RC circuits, but just capacitors. What I'd like you to do for the rest of week 1, or the rest of week 5, up until the end, up until Monday, is finish up the Unit 1 progress check. Again, FRQs and MCQs, especially the FRQ, but give everything a stab. Because although I'm not grading them on marking period 3, I was only allowed to give out 2 new grades on marking period 3. I am going to be giving out all of these progress check grades on marking period 4. So, yes, on marking period 4. So today is, in fact, the last day of marking period 3. Please make sure you've got all this stuff in. I am noting any of the new work. I'm being pretty lenient on excusing that if you need to. That will be a little less true in marking period 4. I understand that this is an international emergency. We're trying to do our best here. So if you're worried about something, if you think you need more time, just send me a message. We'll work it out. I did reopen all the UT quests until Wednesday. If you need me to push out those UT quests again, please just send me a message on Remind, send me an email, and I'll try to open them up. But it is Friday. I have to have grades in relatively soon. So, yeah. So this week with Unit 1 on electrostatics, we're kind of done with our E&M review. We're going to start working our way backwards through mechanics in preparation for the exam. So, again, keep an eye out for how those things are going to go. Which progress checks are going to be graded? The progress checks that are going to be graded are basically going to be all of them, probably just for completion. But I will be looking at, conveniently I'm supposed to put in 8 grades for marking period 4, and conveniently there are 5 units in mechanics and 3 units in E&M. So that makes 5 plus 3 makes 8. So we will be grading all the progress checks for some combination of completion and correctness, probably mostly completion. Because at this point, I just really want to make sure we're doing something that's going to help prepare us for the exam. Speaking of which, so this is, by the way, the last couple weeks have been really chaotic with holidays and this and that. So we're settling into a little bit of a marking period 4 schedule. So the way this is going to go is that on Mondays are going to be reserved for new material. So on Monday, take a look. Monday is also usually for us when things are due. The last week ends and a new week begins. So Monday is the time to wrap up the old week, take a look at the new week, and see what it's got in store and new material. Wednesday we'll have office hours, which means really in the afternoon. I'm just going to be online and available. I'll be doing grading. I'll be answering questions. I'll be communicating with you and making sure that we're all up to speed on Wednesday. And then Friday will be stream day. So you'll have opportunities to contact me multiple times a week. Fresh grades, we'll see. We're just going to make it work. So, but Wednesdays and Fridays, If there's any deviations to the schedule, I will let you know as best I can, but checking my MCPS is always the best way. Or send me a message on Remind. All right. A reminder, exams are still happening, and they're still doing the YouTube reviews and things like that, so please do take a look at those. Our exams are on Monday, May 11th. If you absolutely can't do Monday, May 11th, please talk to Ms. Salvato, and you might be able to do a makeup on June 1st. Monday, May 11th, at noon and 2 p.m. for mechanics and E&M. So make sure that's on your calendar, Monday, May 11th. The format of the exam has changed, obviously, a little bit. There's no multiple choice questions. You will get, for physics, 45 minutes for 2 FRQs. This goes for both mechanics and E&M. Obviously, the topics will be different, but, each of the exams is like this. So you'll get 1 FRQ, which is 25 minutes long, plus an additional 5 minutes to upload your answers. And this is going to be a lot of explaining, justifying, writing. They have explicitly said, at least for one example, that this is a little bit closer to what you might have expected from an AP Physics 1 question. So if you've taken AP Physics 1 before, and many of you have, although certainly not all of you, and some of you it's been a while, you remember the amount of writing and justification and explanation. The questions would very much be like, here's the thing, what does it do? Does it go up? Does it go down? Is it faster? Is it slower? Explain yourself. So I would tend to believe that the questions are going to be closer to that, and that's what they've said. That, excuse me for a second, this first question will be like an AP Physics 1 question, lots of explaining. The second FRQ is going to be shorter, and this is going to be closer to 15 minutes plus 5 to upload. This will be closer to the lab style question we've done. So they'll give you some data or ask you to design an experiment, ask you like, what should I put on my axes so that I can make a line, right? Draw a best fit line, analyze it. So graphical data analysis, lab design, things like that. So I would make sure that you've got, Desmos, you've got Google Sheets, although granted, I guess they want you doing this with a calculator and not on your computer, so maybe don't do that. A lot of graphing, linearization, stuff like that. What quantities and tools do you need? If you need to measure distance, what are you going to use? How are you going to set this up? And linearizing some unusual graphs. So we'll try to get some more practice with that just before the exam, especially for like kinematics and some of the stuff in mechanics, which we haven't done, but which we've kind of already reviewed. We've done the progress checks already. They are going to be open book, open note, and so you can have some notes about how to linearize different functions, and we'll spend some time in that last week before the exam making note cards or notes sheets and working together to do that so that all the equations we need are there, all of the stuff we need is there, and you're not trying to flip through a textbook. So we're going to prepare ourselves. It's going to be different. We're just rolling with what's going on. All right, so let's launch right into it. Here we are with our Unit 2. So this is all about capacitors. This is our progress check FRQ. So this is our Unit 2 FRQ, capacitors. We're going to walk through this one and see what we can do. So it says, and I'm looking at this kind of for the first time. I've printed a couple things off, but I'm not. I've got my data sheet here, but I haven't solved it yet. So here we go. Let's look at this. It asks, in an experiment, a group of students will determine the dielectric constant of paper. Now I happen to remember that that's that K constant that makes capacitors more effective. They have the following materials available, as well as other materials traditionally available in a high school physics lab. They've got aluminum foil, sheets of paper, sheets of plastic, multimeters with the ability to measure capacitance. So A, outline an effective experimental procedure to gather the necessary data that can be used to determine the dielectric constant of paper. Place a check mark next to each item that the students should use. Well, okay. Before we start to get to that, let's talk about experimental design. In experimental design, there's a couple questions that you want to answer. The first question is, what are you varying? What are the things that you're going to change from trial to trial? Maybe it's mass, maybe it's length, maybe it's time. What are the things that how is each trial different? What are you measuring? What's the data point you're going to get for each trial? What things are you holding constant? What are you not changing? And what's the relationship? And it's important to note, you should only vary one thing at a time. So in this experiment, right, you know, we can think about what we could change, but we only want to pick one thing to change. And then what's the relationship? What's the guiding equation or whatever? All right, so if I want to build a capacitor, right, I want to remind myself that I have the ability to measure capacitance, right? And I happen to remember that the capacitance of a big parallel plate capacitor is kappa, that's the dielectric constant, epsilon 0 A over D. That's right off my equation sheet. So I want to determine K. I want to determine K. That's what I want. I can't measure it directly, though. What I can do is I can measure C. So I probably want a multimeter with the ability to measure capacitance. I probably want to, you know, connect my multimeter to whatever capacitor I'm going to build so that I can measure capacitance. And then the question is, how do I want to build it? Well, I need some kind of conducting material for the plates, so I'm probably going to use foil here. I'm going to use 2 sheets of foil. And then in the middle, I'm going to put some paper. I'm going to put, you know, I'm going to fill the gap in between here with paper. Woo. With paper. I don't want to introduce any plastic. And the reason I don't want to introduce plastic is because plastic is also a dielectric, but it's a different dielectric than paper. And I don't want to do that. So what I'm going to do is I'm going to set up a little capacitor with sheets of foil, put some paper in the middle. I'm going to measure the capacitance. And then the question is, what am I varying? And there's 2 viable choices here. I could vary either the area of my plates, so I could make them bigger and smaller from trial to trial, or I could vary the distance. So I could have one trial where they're close together and another trial where they're very far apart. Yeah. So I mean, you could choose either one. For the sake of simplicity, I think it's probably easier to vary the distance. You could vary area just as easily. I think it's easier to vary distance because then you can take the same 2 plates and just fill them with different amounts of paper. Things that I need also, note that I'm probably going to need a ruler to measure the distance and areas of my plates. So my proposal is basically to build a capacitor, to vary the distance by filling it with different amounts of paper, and then measure the capacitance to determine my relationship. This, as it turns out, is I have the key right here. This is a 4-point question. This is 4 points right here. This is 4 points. There's 1 point for making the right selections, and specifically selecting everything that's not plastic. There's a point for drawing a diagram because it specifically says draw a labeled diagram. There's a point for some kind of appropriate procedure, which I did not write out here. And another point for indicating that multiple trials are needed. You always want to have multiple trials. Always, always, always. So, you know, make sure you can answer all of these things and make sure you do multiple trials. In this case. Right, and again, Kevin, this is one of the places where if you didn't include the foil, that's okay. You get 1 point off, right? You know, we're figuring this out. So sometimes things are going to be vague, and that's just kind of the way it is. All right, so let's kind of then go to this next question where it asks you, gives you all of this data here, and then says, and then it says, here's all the trials you did. Which subset of your data do you actually want to use for your thing? Well, I hope it's clear that we only want to use paper. That all of our plastic data is probably no good because, again, we're interested in paper. We're not interested in plastic. So we only really want to use the paper data. And then what I would say is just think about what you said for part A, right? What are you varying? I said that I wanted to hold area constant and only vary the distance. So I'm going to use these four. You could have just as easily, you could have easily said, could have easily, change a, if you wanted to change the area and hold the distance constant, you could use that one. I chose to change the distance and hold the area constant, in which case I wanted to use these four. You probably don't want to use all of them, but you should be consistent with whatever you said before. This was a two-pointer. One for selecting a good subset of data, a subset consistent with whatever you said in part A, and a second point for explaining it. Would it be 4 to 8? It would be 4 to 8. See, I just assumed. Trial 4 kind of bridges the gap. 4 to 8. Great. Okay, so yeah, thank you. 4 to 8. Subset consistent with part A, and then a good explanation. So you want to pick, and again, it's just really important when you're designing experiments, change one thing and one thing only. Explain why the selected trials are most useful. Well, again, they're all paper. They all have different distances, and they all have the same area. So I can really look at this relationship. Okay. Then, it wants you to make a graph. So let me just look at my piece of paper here, 4 through 8. It wants you to make a graph. Well, I am going to draw, before I make my graph, let's think carefully about what I'm doing here. So I know that C is going to be K epsilon 0 A over D, right? If I just do capacitance versus distance, I'm going to get an inverse relationship. I'm going to get something that looks like this, which is not going to be good because the bigger my distance is, the smaller my capacitance is. So I want something that's going to make a line. What I could instead do is look and say, well, if I graph, in this case, 1 over D, if I graph 1 over D, then I can, I get C equals a bunch of numbers times 1 over D. I can kind of, I will get a good graph if I do C versus 1 over D. I do want to make sure to write my units. All my capacitances are in times 10 to the negative 9, which is, what, nanofarads? 1 over D, I kind of got to do a little bit of calculation here. 1 over 1 e negative 4. So here I kind of want to do to the thousands. So this will be, this is an interesting unit. It's meters to the negative 1 times 1,000. Because again, if you just do the things straight up, so this requires a little bit of calculation. But the biggest thing here is C versus 1 over D. The nice thing is if you chose to vary area, you could just do C versus A, so that's probably easier. So let me come look at my capacitances range from 9 to 50, 10, 20, 30, 40. So I can't just do 10, 20, 30, 40, 20, 40, 1, 2, 3, 4, 20, 40. Okay, so this is maybe not the best, but we're going to try it. Yeah, what's the best way to do this? 15 doesn't break up easily. 1, 2, 3, 4. Okay, 20 kind of sucks. I don't like using 20 because I'm not using my graph space effectively. So, but we're just gonna do it. 20, 40, 60, 80. 1 over d, I end up with 10 and 2. So I can go, 2,000, 4,000, 6,000. So I can go 2,000, 4,000, 6,000, 8,000, 10,000. So C versus 1 over D. And now it's a matter of graphing my things. So at that point gives me 9.2. So 5, 10. So I get like 5, 10, something like here. 1 over 4e negative 4 gives me 5, 4, so 4. Yeesh. It's a little awkward. 2.4, 2.8. Okay, so 2.4, so it's like 2.5. So the graph here ends up going 1 over d. The graph does end up a little funky. End up at about 15. 3 negative 4. So I'm making this in real time. I apologize. 2.4, 2.8, 3.2. So a little bit past there. And I get up to 18.9. Okay. Bear with me here. 5, 4.4, 5 is right in here. And I get up to 23.1. And then last but not least, I get all the way out here at 10, and it's like 50. So, and I got some extra little smudges in here. These are not real data points. So it's not the best. It's a little interesting, but I can roll. I can stick a line of best fit through this. I can do my best. It's probably not the best line of best fit I could get. I think moving seems a little bit better for a line of best fit. All right, so that seems okay. C versus A probably is easier to graph, but I like C versus 1 over D just as much. So remember, anytime you're looking for a line, how did I get C versus 1 over D here? What I basically did is I'm looking for, here's my fundamental relationship. I'm looking for something for like y equals slope times x. So here I needed to make y equal to c and x equal to 1 over d. I don't think that they'll necessarily let you use Excel on the exam. I think you need to maybe be comfortable with your calculator. And again, I wouldn't tell them that you're using Excel necessarily or Desmos or whatever, but if you want to use one of those, what I would do is I would not cut and paste a Desmos graph. I would make the graph by hand. And if you need to use a tool to find the line of best fit, I would just say, used my calculator to find a line of best fit or something like that. So I'm not endorsing using these software tools because they probably don't want that. But if you need that extra tool to make sure that you can make a good graph, how you turn it in easily otherwise, that's a really good question. I think they might just want you to draw it on a piece of paper, try to find some graph paper. That's a good question. I'll try to get some clarity on that. All right. Well, in any case, anytime you've made a line, you can always either look at the slope or the intercept. Here, we want to look at the slope, because the slope, right, should be everything that's times what's on our x-coordinate. So our slope here should be all this goodness. So it should be kappa times epsilon 0 times alpha. So let's go ahead and calculate our slope first using the line of best fit, not using the data points. So what do we get? We get a slope of, I'm going to use these 2 points. So my rise looks like 5, 10, this looks like 10 nanofarads for my slope. So I just want to be very clear about this, that is 10 times 10 to the negative 9th farads. I'm careful about my units. And that this difference is 2, and this is in thousands. You know, and it's got units of inverse meters, which is kind of awkward. Super awkward. So 10 times 10 to the negative 9th divided by 2,000 gives me a slope here of like 5 times 10 to the negative 12. Now that should be equal to kappa times epsilon 0, I happen to know, is 8.85 times 10 to the negative 12. And our area for all of these is 0.25. So if I do a little bit of solving, I divide by 0.25, and then I divide by epsilon 0. I get a K of about 2.26. I get a K of about 2.26. I get a K of about 2.26. Let's see what they say. They suggest here making the graph accurately with, oh, I left out a part, B2, my apologies. That was 1 point for indicating quantities that can make a straight line. C, and so if you got 2 million, my guess is that we weren't careful about our units, right? So just note on the graph, and again, you're not really going to lose that many points for that, because if you did mislabeled the graph, right? So remember that your capacitance is times 10 to the negative 9th farads, and that if you do 1 over d, that this is really like, you know, 2,000, 4,000, you know, 6,000. 8,000. So just be very, very careful with your orders of magnitude here. This is a kind of awkward one. No, 2 million is not bad, because, and I know this seems silly, that tells me that you got the 2, but didn't include the correct like exponents, the correct like order powers of 10. The graph itself is 3 points, 1 for doing it, or sorry, 1 for axes with units. Remember, don't leave off axis labels. 1 for a good scale and plotting, and 1 for a best fit line. So remember, if you're not sure what's going to give you the right graph, just make a graph. Like, make as good a graph as you can. For then finding it, I just want to flex a little bit. I'm sorry, in these dark times I need to flex a little bit. Finding K, finding the dielectric constant, is in fact, you know, they have you do some linear, you know, they say you could use linear regression or whatever. It's 2 points, 1 for calculating the slope, and 1 for correctly relating it to K. The example that value that they give is on the key is, and let me make sure that you can read this. The example that they give on the key is in fact 2.26. So I feel pretty good about that. You know, we all need something to feel good about in these times. So, you know, it's it seems like I did an okay job making my graph. If you make your graph C versus A instead, your graph is probably a little easier to make. So, yeah. All right. Then it asks us to do some other things, to sketch some other graphs. 2.26 million. Yeah, if you got 2.26 million, again, that's just being very careful with the exponents. You know, making sure you've got the times 10 to the negative 9th above, you know, thousands on the bottom. You know, your slope should be times 10 to the negative 12. So I would just go back and make sure that you've got kind of all the right times 10 to the on there. But if you're getting 2.26 million, that means you are doing the vast majority of it right. On the axes below, sketch the capacitance C as functions of plate separation. So this is really just, hey, can you sketch this, you know, K epsilon 0 A over D, right? So if I'm just varying D, right, C goes as 1 over D. So I should get something that looks like this. You know, should look like a 1 over X kind of deal. Versus A, right? Well, it's linear in A. So it should just be literally a straight line. And you should get a straight line also here, because again, K and A are on the same footing here. So you should get like an inverse graph and then 2 linear graphs. And that's 3 points, again, for those. This should have nice asymptotes, right? So don't make sure that it doesn't touch anywhere. But this is +3 for those 3. And that is that. Okay. Let's see, how much more time do we have today? I've got, let's see, 2:30. I got another 10 minutes or so. So we're gonna pause for a moment. And then I pulled out a couple of these Unit 2 multiple choice questions. So we'll take a look at as many of these as we can get to in the time that we have. There's no multiple choice section on the exam, of course, but they're still pretty good intuition questions. So this first one is kind of not about capacitors at all, and is instead asking about electric fields. So we have a plus Q charge here, and an isolated conducting sphere of radius r. And we're looking at the electric field right here at the center. Well, you might just be tempted to use KQ over r squared, but remember, we are inside a conducting sphere. Remember your voltage mapping lab? What did the electric field look like inside your ring? You should expect actually that the electric field everywhere inside here is 0. Remember, the charges on your conducting sphere are going to move around. You'll get a bunch of negative charges over here and positive charges over here, so that the electric field will kind of like and like bend onto the sphere. And the electric field inside is 0. So if you're inside a conductor, the electric field does its best to be 0, assuming there's no charge in there. If there's actually a charge in here, if there's like a plus Q in here, then it's a little different. But the conducting surfaces screen out all external charges, all external electric fields. Q5, shells at equal potential. So equilibrium is established. What's the correct relationship? Well, remember, if we want the voltage to be equal, because that's the only way they come to equilibrium, kind of equal pressures. Remember that voltage goes like, you know, KQ over R. So what we'll find is that we'll find little q over little r equals big Q over big R. That the smaller sphere can kind of fit less charge because it's a little bit more crowded. Charges have to maintain good social distance. So the ratios will stay the same to make sure that the voltages are the same. These are the most popular ones that were submitted. Number 19, skipping all the way here. Oops, I meant to cover these up. These ones are a little strange. So we've got a parallel plate capacitor that's charged by connecting it to a battery. And it ends up with an energy UE. How much work was needed to charge the capacitor? Well, if it started out with 0 energy, right? If energy initial was 0 and energy final is UE, right? Well, where the heck did that energy come from? We had to do that much work, you know? Yeah, there's also an integral. Yeah, so B is not entirely true. B was the most popular answer, which has the correct answer of UE. But in all physical situations, work is not done. Work is usually equal to the change in kinetic energy. It is equal to the energy you're putting into a system, but not necessarily equal to the final potential energy. In this case, we come to a steady state. Nothing's moving. There's no energy associated with current. It's just all potential energy. So yeah, that one was a little strange. But B has kind of the right answer, but a suspect justification. 20 says a capacitor is connected to an ideal battery, allowed to charge completely, and then isolated from the battery. So it's got, you know, some Q equals CV. And then you insert a dielectric material with a K of 3 in here. And which of the following correctly describes the process of inserting this thing? I gotta kind of pull up the multiple choice. Excuse me, I apologize. My thing logged out. My AP classroom thing logged me out. Yes, this is the content you are here for. Me scrolling around through, staring blankly at the screen while I look at progress checks. So this is number 20 on the Unit 2 progress check. Unit 2 progress check, MCQ. Question number 20 gives us some options. Specifically, wait for it, the suspense. Okay, so part of the question is, what's going to happen is, all of the answers kind of come down to one thing. Is the capacitor going to like suck the dielectric in, or is it going to be hard to put the dielectric in? So let's ask ourselves, first of all, what happens to energy, right? Systems want to go to a lower energy state. So our initial energy, right, is 1/2 CV squared. Or sometimes if you do Q equals CV, you can write this as 1/2 QV. Right, 1/2 QV. 1/2 QV. The final energy, right, should still be 1/2 QV. And so the question is Q initial, V initial, Q final, V final. So the question is, what happens to our energy? I guess actually it's even clearer. Let's 1/2 QV is actually not my favorite here. Let's put this in a different way. It is in fact, what is it? If I substitute V equals Q over C, I end up with 1/2 Q squared over C. So I like this. I like this version better. Q final squared over C squared over C final. Now notice what happens, right? The Q stays the same. This thing is now isolated from the battery. There's nowhere for charges to go. I've got plus Q on this side, minus Q on that side. That's not going to change. But what happens when I insert this dielectric is that my capacitance goes up by a factor of 3, right? So if my capacitance goes up, what happens is my final energy actually goes down. The energy stored in my capacitor decreases. And so what that tells me is that my capacitor wants this dielectric in there. It wants, that dielectric wants, wants to lower its energy. So it's actually going to pull the dielectric in. If you were doing this experiment, you would actually feel a tug trying to put that dielectric. It would pull the dielectric in, and it would be hard to get it back out. So it will pull the dielectric in, and it'll actually decrease the potential energy in the circuit. It'll decrease the potential energy. And you might think, well, why is it decreasing the energy? I thought that capacitors that dielectrics made things store more. The way the dielectric works is that it allows more. It basically, remember, capacitance is Q over V. It allows lower V for the same Q. So it basically says it makes it less costly. It lets you get the same amount of charge with less energy. So this is pull dielectric in and 1/3 the energy. And decreases the energy in your same charge, less energy. You can kind of think of it, some of that energy was used up sucking the dielectric in. Dielectric slab and capacitance, again, I'm giving away the right answer here. Isolated parallel plate capacitor. You should find capacitance goes up. And again, if voltage goes down, electric field also goes down. So we should find that capacitance goes up and electric field goes down. If you said, most people said capacitance will increase, that's good. Remember, it weakens the electric field. It makes it easier to charge up. Here we got another one, which I forgot to put a spoiler tag on. We're going to be done in just a couple minutes. I want to be off by 2:30 so that people can watch the Governor Hogan press conference. So any of these ones we miss, we can always go over next week. I'm not going to close these progress checks. An air-filled parallel plate capacitor. So it's connected to a battery. So in this case, the charge can change. So it's got a battery of voltage V, and it's connected to a capacitor. And it's got Q equals CV. Material dielectric K equals 2 is inserted. So what's going to happen? Well, the charge should go up, right? The charge should double because our C is doubling. And you might say, but shouldn't voltage go down? Well, in this case, we're connected to the battery, right? The battery is going to make sure that if I follow my loop law, my battery is going to make sure that the voltage across my plates is the same. And if the voltage across my plates is the same, the electric field is going to be the same. So what should happen is that I should double my charge and get the same electric field. And that's, again, that's the secret of dielectrics, right? Is they give you more charge for your electric field. They give you more charge for the same voltage. 2Q and 2E actually is the same capacitance, is no better, right? You're doubling the strength of your field and getting twice as much charge. That's what you'd expect. If you can get twice as much charge for the same electric field, now you're doing a good job. Now you're doing better. All right, we'll do one more and then we'll close off. Again, we've got a parallel plate capacitor with plate area A and separation distance D. And it's got a dielectric in here. K equals 2. This is the worst capacitor I've ever drawn in my life. Isolated, fully charged. And you've got, 20 joules of energy in here. And then you slowly remove the material from between the plates. what you're going to find is that the energy stored in the capacitor should double. Why should the energy double? Well, remember in our previous question how it went down? You're going to try to pull this dielectric out, and you're going to feel that it doesn't want to let go. You're going to have to put in a bunch of work to tear that dielectric out from in between the plates. That work that you put in will be exactly enough to double the energy here. So you should find it will be exactly equal to the change in energy between the two systems. You could also kind of see, you could also look at the energy exactly because, again, if it's isolated, the charge isn't going to change, right? And so your energy, 1/2 Q squared over C, right? If you remove the dielectric, the C goes down, energy goes up. So isolated versus not isolated are a little different. All right, we are going to stop here. I know there's more that people wanted to go over. We'll hopefully get to them next week. In any case, I'm going to be back with aerospace in about half an hour. I hope you're all staying safe. Remember, end of marking period 3, get those labs in, get the UT quests done. If you need anything, send me a message on Remind, send me an email. Today is Friday. We're going to do our best. And I miss you all. Bye.